Right, chapter 7, we're going to start today. It's the quantitative. Remember, quantitative means number, composition of compounds. In other words, what amount of stuff do we have in a compound? Okay, here it is showing you pearls. They're actually calcium carbonate, which is the same thing that makes up Tums. But, under certain conditions, they get a different color and they're worth a small fortune. So they can measure those out and sell them for a small fortune. Sorry about that. I thought I took that off. Convenient ways of counting. Now, every uh, system, I guess, has kind of its own way of counting. Like, why do we sell eggs by a dozen? I guess that's just the way the carton worked. Or the same, like a bakery. Why don't they sell things by 10 or 20 or whatever? They sell things by a dozen. So it's just what happens with the system. Again, a ream of paper is 500 sheets. Okay, so every system kind of has its way. So chemistry did the same thing. Oh, here's a gross of pencils. If you didn't know, a gross is 144. It's 12 times 12. So when we're talking about atoms, remember atoms are so tiny. There's no way you can actually like physically weigh them or anything. So what they did was they came up for a system that was uniform that everybody could use to measure things, okay? So chemists have their own system, all right? If you really wanted to know the amount of atoms in a mole is a unit of measurement, okay? If you want a mole of any substance, it's whatever their mass is from the periodic table. So if you look at carbon, carbon's mass is 12. So if I weigh out 12 grams of carbon, I have 1 mole. If I weigh out, like calcium's mass is 40. If I weigh out 40 grams of calcium, I have 1 mole. So 1 mole of any substance is whatever its mass is from the periodic table. Okay, so if I have my 1 mole of calcium, if I wanted to figure out, if I wanted to count all the atoms that are in that 1 mole, I would die before I got to that number. And I'm old, but even you guys would die before you got to that number, and you're not old. So it's a huge number. If you look here, 6.02 times 10 to the 23rd. So take this number and add, 20 zeros. You're talking like 602 hexillion. So it was mathematically, they figured out mathematically, there's no way anybody counted. And the guy that did it, his name was Amadeus Avogadro. So it's Avogadro's number. When I was in high school, we used to call it Avogadro's number. But anyway, Avogadro's number is the number of atoms in 1 mole of any substance. And it doesn't matter what substance it is, okay? If you're talking about an element, you're talking about compound, whatever. If you have 1 mole of any substance, that's how many atoms you have in it. Okay, so again, 1 mole of anything contains Avogadro's number. We just use 6.02 times 10 to the 23rd. So if we're talking about atoms, okay, that would be an element. If we're talking about molecules, that's a compound. So if we're talking about water, water has a mass of 1 mole is 18 grams, and I'll show you how to do that here in a little bit. But 18 grams, so if I have 18 grams of water, if I counted all the molecules in there, because now we don't have atoms anymore because they combine, remember, there would be Avogadro's number, 6.02 times 10 to the 23rd. If you were doing ions like in salt, same deal. So if you have 1 mole of any substance, it has Avogadro's number of atoms, molecules, or ions. Okay, so we can use that as a conversion factor. We've done dimensional analysis where you convert things from one to the other basically by multiplying by 1. This is like multiplying by 1. It depends on if I'm starting with moles and I want to find atoms or molecules or ions or whatever, I would use this because moles would cancel out. If I'm starting with the number of particles, the number of molecules or atoms or whatever, and I want to find moles, I would do it the reverse. Because remember, whatever you start with, you want it on the bottom so it cancels out. So this is a conversion factor. And again, I just use 6.02 times 10 to the 23rd. If you want to use 6.022, go for it. But, it doesn't really make that much difference. Okay, so calculate the number of atoms in 2.4 moles of sodium. All right, so remember when we do these, we write down what we know. Now here it says 2.5 and here it says 2.4. Weird, right? Why? Oh, now it went back to 2.4. I'll have to switch that. I didn't do that, you guys. Anyway, write down what you knew. No, 2.4 moles of sodium. That's what I have. Okay, so which one of these am I going to use? Well, I'm going to use this one because moles are on the bottom. Okay, so I'm going to put moles on the bottom, and 1 mole of sodium, 1 mole of anything, it doesn't matter, has Avogadro's number of atoms. Okay, So moles cancel out. And so I'm going to take 2.4 times 6.02, and then I got to tack on my 10 to the 23rd. Sorry about that, itchy nose. Okay, I'm going to get 14 times 10 to the 23rd. Remember, we have to write things in proper scientific notation. So I would move the decimal over 1 and make this number, instead of 14, 1.4. That's proper scientific notation. Excuse me. And then I'd make this number larger. So in 2.4 moles of sodium, there's 1.4 times 10 to the 24th sodium atoms. Okay. How many molecules of HCl are present? Hydrochloric acid. Okay. Now, again, now we got a compound, but the number's the same. Okay. It doesn't matter if it's a compound or an element or whatever. When you're talking about the number of molecules or the number of atoms, the number's the same. So we'll set it up down here. Oh, shoot, you guys, sorry. I thought that was set up on there. But the way I would set this up is I would have this times, I'd put 1 mole on top, and I'd put Avogadro's number on the bottom. So it takes 4.3 divided by 6.02. So you're going to have a number that's like, what, 0.7 something? Okay. And then 10 to the 23rd, and I have 10 to the 23rd on the bottom. They are going to cancel each other out. So that's where you get this. Okay. Remember, if you're dividing scientific exponents, you subtract the exponents. If you're multiplying, you add the exponents. Okay. All right. So another thing we got to do when we're talking about units of measuring in chemistry, they made it convenient to count mass because, like I said, you can't weigh out just an atom. They're just too small. We don't have any kind of scale that would do that. So what they did here, they're talking about a canning recipe, and you need 150 apples to be, prepared, peeled, and cored. So if the average mass of an individual apple is 235, how many kilograms? So you can convert that, okay? That's kind of what they did in chemistry with, like I was saying, 1 mole. The way to measure the amount of substance in chemistry is a mole. And 1 mole of any substance is whatever its mass is from the periodic table. So it's their way of kind of taking the average mass and converting it to something we can actually measure. Okay, so here's your, if I have 150 apples, apples, 35 grams. If I want to change it to kilograms, these are just conversions, okay? That's all you do when you're doing conversions, is you're multiplying by 1. They said right here, an individual apple is 235, and we got to change it to kilograms. I know 1 kilogram is 1,000 grams, okay? So you should buy 35 kilograms of apples. Well, they've done this with elements and compounds as well. They've bumped them up to units that we can use, units we can measure. Because like I said, there's no way you can measure out individual atoms. They're just too tiny. Okay, so by counting the atoms and using the mass, again, individual atoms are too small. So that's why they use their system of the mole. The amount of substance is a mole. And again, that's whatever the mass is from the periodic table. Okay, the average mass of an atom we know is atomic mass units. Well, what we did, or what I shouldn't say we did, I didn't have anything to do with it, honest, you guys. The average mass of 1 mole of atoms, their atomic mass, is their molar mass. And again, that's what we find on the periodic table. So 1 mole of atoms is whatever their atomic mass is. And we change it to grams now. We can get rid of the AMU. Okay, and we also know 1 mole of atoms has Avogadro's number of atoms. So again, if I have 1 mole of any substance, it's whatever its mass is from the periodic table. If I want 1 mole of phosphorus, I look phosphorus up on the periodic table and I see its mass is 31 grams. So I measure out 31 grams of phosphorus. Now, if I sat and I counted in that 31 grams all the atoms, I would get Avogadro's number. Okay, that's how it works. All right, so they're all equal to each other. And those are conversions. Oh, I really thought I shut that off, you guys. Here's another example. Like hydrogen has a mass of 1. And again, you guys, we usually round. You don't have to use 1.008. 1 is fine. That's its mass from the periodic table. So that's its molar mass. And this is the number of the atoms. This number comes right off the periodic table. Okay, and again, we tend to round. We'd use 24 and 23 and so on and so forth. But you notice this number never changes. 1 mole of any substance has Avogadro's number of atoms. 1 mole of any substance is whatever its mass is from the periodic table. Oh, I really got to get rid of that. Sorry, guys. Okay, calculate the mass of 2.4 moles of carbon. Okay, well, I know that carbon has a mass of 12. I can look that up in the periodic table. I got everything I need now. So we're going to use one of those conversion factors, depending on, well, we're going to start with moles. So I'm going to use this one because I want moles to be on the bottom. So I write down what I know. I have 2.4 moles of carbon. Now I want to get rid of moles of carbon. And I know by looking on the periodic table, carbon has a mass. And again, I'm just going to use 12. Okay, so now I got rid of moles. Okay, so I'm just going to take 2.4 times 12. And I get 29. So if I weigh out, if I measure out 29 grams of carbon by using my scale, my electronic scale, we have those in the lab if we ever get to get there, you guys. Anyway, if I get 29 grams, that is 2.4 moles. Okay, so whenever you're converting from moles to grams, you start with what you know. Put moles on the bottom. 1 mole of carbon has a mass of 12. This is just like multiplying by 1. And that's how you get your 29. You just multiply the numbers on top. Okay. What is the correct setup to calculate the number of moles of atoms? Okay, so now we're looking for numbers of atoms, okay? The number of moles of atoms. But we're just looking for moles. They're trying to make it tricky. Moles is moles, okay? So we're trying to find the number of moles of atoms, and we have 3.52 grams of aluminum. So if we start with aluminum, we want grams on the bottom. So we know this isn't any good. And honestly, this isn't any good because we're looking for moles. I know they say moles of atoms, but it doesn't say number of atoms. It says moles of atoms. Okay, so all we would do is take the mass they give us and we'd put grams. This comes right off your periodic table. And again, if you want to use 27, please go for it. Okay, this is all you'd have to do. This we'd have grams and moles. We'd have grams squared over moles. That's not a unit we want to deal with it. And here they're talking about atoms, and it says moles of atoms. So we're just looking for moles. If we want this number, it would be number of atoms. Tricky, I know. Okay. Okay, calculate the number of atoms in 36 grams of carbon. So we'd go 36 grams times 1 mole on top. Carbon atomic mass is 12, so it'd just be 36 divided by 12. What would that be, like 3? So we got a plan. Okay, and again, calculate the, number of atoms. We're going to have to do one more step. So I got the number of moles, but I got to do one more step, don't I? Because if you're looking for grams to atoms or atoms to grams, it's not one step. All the rest of them are just one step. But unfortunately, we have to do 2 steps because it's kind of like, remember when we were changing years into minutes? Well, there's not a conversion of, I don't know how many minutes there are in a year, but I know how many days and how many hours and minutes. So sometimes you have to use more than one conversion factor. So here, you take what you know, you're 36, 1 mole here, 12. This is where I got my 3. And then we do one more step. Now I got rid of grams, I have moles, I want to get rid of moles, and I know 1 mole of any substance has this. So what I'm going to do is go with 36 times 6.02 divided by 12, and you get 18. Okay, and again, you got to tack this on. You can't just forget about this. Well, we can't leave it as 18 times 10 to the 23rd. That's improper scientific notation. So what I do is I move the decimal over. I make this 1.8. I made this number smaller, so I make this number larger. That's why it's 1.8 times 10 to the 24th. So that's how many atoms there are in 36 grams of carbon. And that makes sense because if 1 mole is 12, 1 mole would have Avogadro's number. It should be a bigger number because there's more than 1 mole here, and it is. Okay, that's kind of a way you can check to see if you're on the right track. Okay, here's another one, and this is probably our last one, you guys, because we're going to be at 15. Okay, what is the mass? Okay, now we're going to start with atoms of lead. Okay, so I'd start with this, and I'd take this and I change this. I put 1 mole over Avogadro's number, and then I'd multiply by the mass of this, and I would say it's half of 207. So what is that? I think it's A. Oh, yep. Oh, and I didn't do it. Sorry. Why I got that, you guys, is 3.01 divided by 6.02 is going to be 0.5. Okay, these are going to cancel out. So I know because they cancel out that I have half of this. That's where I got the 104 from. Okay, and I think we're just about done. I'm just about at 15 minutes. So we're going to quit right there, and then we'll pick it up. So now we're going to work on some conversions, you guys. Good luck, and I'll talk to you soon.